Welcome back. Today's lecture is all about understanding blackbody light curves. Okay, to get us started, I'm going to draw a graph, and the vertical axis I'm going to label as energy output. And so greater energy will be high up on the graph, and lower energy output will be low down on the graph. And on the horizontal axis, I'm going to label wavelength with longer wavelengths towards the right and short wavelengths on the left towards the origin of the two axes. And I'm going to draw in the little section of light that is visible light on this wavelength axis. And then I'm going to label the other forms of light, UV, X-ray, and gamma at the shorter wavelength ends, and IR, microwave, and radio out at the long wavelength ends. And this is going to be a graph that we use quite a bit, so I'm going to say all of those things really quickly again. This is an energy output on the vertical axis with greatest energy towards the top and least energy towards the bottom, and its wavelength on the horizontal axis with longest wavelengths out towards the right and shortest wavelengths on the left at the origin of the two axes. Okay, I'm going to draw a curve on this graph, and so let me put a little dotted line in here and draw a curve in. And now let's talk about this graph that I've drawn. The object represented by this light curve on our energy output versus wavelength graph gives off very little gamma radiation, a little bit more X-ray radiation, and we can tell because the curve's getting taller at X-ray than it was at gamma, and then it's giving off quite a bit more UV, but its greatest energy output occurs over the visible wavelengths, with its greatest or peak energy output happening at the wavelength of yellow light. And then as we move to longer and longer wavelengths, we see it gives off a little bit less orange, a little bit less red, and then it's still giving off quite a bit of infrared radiation, but the amount of energy output is continually decreasing as we move to longer and longer wavelengths with less microwave and even less radio as we move out to the longest wavelengths of light. Okay, let's investigate this light curve and this graph a little more. I'm going to start off by identifying the location on the wavelength axis where UV light just begins, so wavelength's just shorter than visible light, and I'm going to draw a dotted line there, and I'm going to identify the part of the light curve that corresponds with that wavelength of UV light, and I'm going to draw a horizontal line over to show where the amount of energy output of this object at that UV wavelength is. And then I'm going to identify two more locations. I'm going to identify on the wavelength axis the location where infrared just begins, so wavelengths just longer than red visible light, and I'm again going to identify on the curve where the amount of energy output is for the beginning of infrared, and I'll draw a horizontal line over to the energy output graph to show that that's how much energy output is occurring at infrared wavelengths. And then I'm going to last identify again that center, or rather the peak of the light curve that is occurring at yellow wavelengths of light, and show that that is indeed the wavelength of light that is giving off the greatest amount of energy. So if we were to kind of describe these three different wavelengths that have been identified, we'd say this object is giving off the majority, or the greatest amount rather, of its energy at yellow wavelengths of visible light. In addition, we'd identify or say that the wavelength of infrared light that has been identified has a much greater energy output at that infrared wavelength than this object would have at the UV wavelength that has been identified. And we see that because the peak is much taller at the infrared wavelength that's been identified than it is for the UV wavelength that has been identified. So now I want to introduce a way of identifying or thinking and communicating about the information of this light curve. So I'm going to draw this little arrow in here and say that that yellow wavelength of visible light, that is the wavelength of the peak of this light curve. Okay, so now I want to kind of bring this all together. This light curve, as I'm calling it, has a name. It's called a blackbody curve. So this is a blackbody curve, and blackbody curves are an energy output versus wavelength graph, and the wavelength of the peak of this curve is an indication of the temperature of the object that is represented by this light curve. Okay, so this is a really important idea, and I'm going to say that again. The wavelength of the peak, another way of saying that is if you look at the wavelength axis and you imagine putting your finger on the wavelength axis right underneath where the peak in the curve occurs, that wavelength, which in this case is yellow light, indicates how hot or cold the object will be. So the way in which we will make comparisons between temperature of objects when we see light curves like this is we will look at where the maximum energy output is, or peak, and then we'll look down to the wavelength axis and identify which wavelength the peak is happening at, and the wavelength of the peak will be an indication of the object's temperature. And we talked about this earlier, where in the prior video lecture I showed you how to think about temperature and color before, and I said that imagine you had an object that was giving off most of its energy at blue or short wavelength light. That object would be giving off very, very energetic photons overall, and we would say that that object is hot. In contrast, you could imagine an object that gives off the majority of its energy at long wavelengths of light, or red light perhaps. And so since that object is giving off weaker or lower energy photons overall, we would say that that object is cool. So the general rule is wherever the peak occurs, it tells you about temperature, and objects who have a peak at shorter wavelengths will be hotter, and objects that have a peak energy output at longer wavelengths will be cooler. And so we will investigate that next. Okay, so to investigate this relationship between the peak in the wavelength of an object's light curve and its temperature, and also its color, I'm going to draw another light curve. So this light curve has its peak occurring at the wavelength of infrared light. So here I am identifying with this arrow that the wavelength of the peak is in infrared, or IR. And the general way to interpret this would be to say that this object gives off mostly low energy photons as a result of its peak being at relatively long wavelengths, and therefore it would have a low temperature. In addition, the wavelength of visible light that it gives off most is at the red light wavelength, which I identify by drawing this line up from where red light occurs up to the point on the curve where red light happens, and we see that that is the greatest amount of visible light this object will give off. So this object would appear reddish in color. I'm going to make that point again. While this object's peak wavelength is occurring at infrared light, the wavelength of visible light that it gives off most is red light, and therefore the object would appear reddish in color. So I'll just draw this little red object here to say this could be the light curve of that red object. Okay, now let's move to investigating another light curve. I'm going to draw another light curve here. And what we have is an object whose peak energy output occurs just before X-ray starts. So I'm going to identify that with this little arrow and say that the wavelength of the peak of the energy output of this object, it gives off mostly high energy photons, and as a result this object would be hot. Again, because the wavelength that the peak occurs at happens at a short wavelength of light, in this case out just at the edge of UV, right where X-ray starts, we would say that this object again gives off mostly high energy photons and would therefore be hot. Now to think about the color of this object, I'm going to draw a little line in here right at the edge of where this object gives off its greatest amount of visible light. And so we would say that the wavelength of visible light that this object gives off most is blue light. I tend to just say blue, whether it's violet or indigo or blue, I just say blue. So the object would appear bluish in color. So again, the wavelength of visible light this object gives off most is blue light. So the object would appear bluish. Okay, as a last step to today's lecture, let's imagine another energy output versus wavelength graph, and I'll draw in the visible light spectrum part, and I'll draw in where UV and X-ray and gamma ray happen, as well as IR and radio. And I'm going to draw two curves. Here's curve A, and then another curve B. And as we take a look at these curves, I want you to start thinking about all of these different properties of light and comparisons between objects that you can now make by just interpreting how these two different blackbody curves are drawn and where they occur on the wavelength axis and how tall they are at different wavelengths of light. So I'd like you to make a comparison. I want to know, in terms of the wavelength of the peak for curve A versus the wavelength of the peak for curve B, which one has the greater or longer wavelength, or which one has the shorter or less than, if you will, wavelength of light, or are they equal at their peaks? Also think about the resulting temperature that you would compare for these two objects A and B. And again, just use your greater than or your less than, greater than, or equal to symbols. And also the energy output of object A versus the energy output of object B. And then also which, if either of the objects, would appear bluer, and which of the objects might appear redder in color. And lastly, which of the objects is giving off more red light? And so I'd like you to think about the comparisons of each of these physical quantities for the two objects A and B. So again, I want you to think about your answers to those comparisons about the two different light curves, and I want you to also think about how you'd explain your answers and the reasoning behind your answers to one of your classmates. And we'll give you just a little bit of time to think about that. Okay, let's start making some comparisons here between the properties of the light curves and the objects they represent for blackbody curve or light curve A versus blackbody curve or light curve B. First off, we have the wavelength that the peak occurs at. If we put our finger or think about where the peak of curve A occurs and follow it down to the wavelength axis, we'll see that the wavelength of the peak of curve A occurs at UV light, whereas the wavelength for the peak, or where the peak occurs in terms of on the wavelength axis for curve B, that is happening at red or infrared light. So since UV light is shorter wavelength than infrared light, we will say that the wavelength of the peak for A is less than the wavelength of the peak for B. In terms of temperature, we have to think about the rule that we've developed, which is objects which give off or peak at short wavelengths of light are much hotter than objects that peak or give off mostly long wavelength light. So since the peak for A is at shorter, higher energy photons, we'll say that that object is much hotter than the temperature of object B, which peaks and gives off mostly low energy photons. With regard to the energy output for both objects, the light curve for A indicates that it is giving off much more energy at all wavelengths than object B is. So the energy output for A is much greater than the energy output for B, and that is just represented by the height of the curves that are drawn for each object. In terms of color, remember that the idea is that you look at a light curve, we'll look at A first, and note where it gives off most of its visible light, and the curve A is tallest and giving off most of its energy at the blue end of the spectrum, so we would say that object A is bluer. And if we look at object B, we see that it's giving off most of the visible light that it's giving off. It's mostly at red wavelengths. So we would say that object B is red. So I'm going to draw in a little red dot for object B and a little blue dot, bigger blue dot, for object A, indicating that object A would appear blue. It is hotter than the smaller red object that is represented for the light curve for object B. Now, in terms of which object is actually giving off more red light, this is a little more complicated. If we draw in a dotted line right at the red wavelength of light and we let it intersect both light curve A and light curve B, what we see is that even though object A would appear blue, it's giving off a lot of red light. In fact, it's giving off more red light than object B, even though object B appears red. Object A is giving off more red light than object B. Okay, that will do it for today's lecture, and we'll see you in class.